Okay, Calc 2, Lecture 29, Infinite Sequences and Series, Sequences Continue. So I introduced arithmetic and geometric sequences last time, and I also found some kind of limit for a special kind of geometric sequence. Now, a sequence in mathematics has very rigorous definition, but we can define it this way, or let's say explain it this way. It is a list of numbers indexed by a countable set, usually the integers. So you can index it by any countable set, but as I say here, usually you use integers, and most often you're using, say, integers bigger than or equal to 0 or bigger than 1, say. But anyway, these are two examples. One of them starts at 1, so the index, this one starts at 1, so that's A1, A2, A3, and so on. It can stop. It can stop at some point. It's like a finite sequence. So if it stops here, finite. If it continues, infinite. Okay, so the difference is finite sequence stops at some point, infinite continues. And we are interested in the infinite one, not the finite. But in order to study the infinite one, we need the finite ones. This one starts at negative 50. One might say, why do we use negative 50? Sometimes it's useful to use index like that, indices like that, starting at some negative number or something. Well, anyway, so examples, we saw two examples last time, arithmetic sequence and geometric sequence. Well, this is another one. This is also some kind of geometric sequence, but well, this is geometric sequence. So let me see if I can give you another one which is not a geometric sequence. So yeah, I can write this. Why do I write two? Okay, so let's write this. Well, it's simple. 1/2, 1/3, 1/4, and this is 1/n. So this is a nice sequence, and we will see it in like the series. This appears in study of infinite series a lot. But anyway, so this is an example. It's neither of them. Okay. Now, if we look at this one, especially this one, remember yesterday I talked about the sum of a geometric sequence, and I showed that in some cases that sum converges when it's an infinite geometric sequence. Now let's look at this one. I'm not adding them, but you can see that this, in fact, is these numbers are going down. So let me graph this thing for you. In fact, there is what we call a sequential graph on most calculators, including the TIs. There is sequential, SEQ. So if I graph this thing, which AN is in fact 1/n, we usually write the general term. And we also indicate where it starts. So I say n starts at 1, 2, ... It means that n starts at 1. Definitely it cannot start at 0 because 1/0 is not defined. So that's the general term, and this is we should say where the index starts and how it goes on. So this index starts at 1 and then goes to 2 and go on to infinite. Now, how do we graph this thing? It's very simple. So this is 0. We didn't start at 0, but we started at 1, say 2, and then 3, and 4, and so on. And at 1 it is say 1, at 2 it is 1/2, then 1/3, and this. So this is the sequence. And you can see that this is so this is 1, and this is 1/2, 1/3, and so on. And you can see that these points, they are getting closer and closer to this n-axis. Let's call this n-axis. although we don't have anything in between, but we can call this n-axis, where we will see that it's like the x-axis, and this is like the an axis, right? So we see that these points, they get closer and closer to this n-axis, which means that the an is getting smaller. So the an is getting smaller, and it gives us a sense that sense of limit. Limit is like that. As n goes to infinity, what's happening? So we can talk about limit of an, and we usually write it like this, the same way that we had the limits in Calc 1. So that's the limit of an. So we say that the limit of an is L. So we say definition. We say that this is L. If as n goes to infinity, an gets closer and closer to n, right? So it means that as n gets large, an gets closer to L. Okay? So I can write a rigorous definition, but I don't think there's any need for that, and I leave that to a more advanced course. If you ever take a more advanced course in mathematics, definitely they start with sequences, and they define sequences and the limit of a sequence very carefully. But what we need is just that feeling that what's happening. Okay. Let me erase this and give you some. There are so many interesting theorems, in fact, regarding, say, limit of a sequence. So limit of a sequence is crucial in mathematics. So, well, I didn't define it carefully, but I gave you some feeling what's going on. And I remember I used absolute value. It means that a sequence can jump up and down. Now, how does this happen? So let's introduce this -1 to power n. What is -1 to power n? This is in fact like a sign rather than, although that's 1, -1, 1, -1. When you multiply it by a number, it basically changes the sign of the number. Or alternates. So that's like alternating things. So let's say an is this, and let's say n starts at 1. So if this happens, what does it look like? It is -1, -1 to power 1, then it is 1, -1, 1, -1, and so on. So as you see, this is alternating. So if I have alternating. Now, alternating sequences and series are amazingly important. Maybe you realize at the beginning of the previous lecture when I was writing the series for sine and cosine, both of them are alternating series. So it's plus minus, plus minus, plus minus. In fact, that alternating, it makes the series convergent. If it has certain properties, it is a lot more prone to be convergent than sequences that are either just positive or negative. Well, anyway, now when you see this thing, for example, if I write it like this, an, if I write something like this, -1 to power n times 1 over n, and 1, 2, dot, 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 then this is the what? This starts at -1, in fact, then it is +1/2, then it is -1/3, then it is +1/4, and -1/5, and so on. So this is alternating again. Okay. And now if you graph this one, unlike the previous one, this is jumping up and down. So this one jumps up and down. So it starts here, then goes here, then here, then here. So it jumps up and down, and by up and down I mean above and below the x-axis, this one. So, but as you see, it again gets closer and closer to 0. As n gets larger and larger, either from negative or positive side, it gets closer and closer to 0. And in fact, the limit of this one is also 0. And that's why I use absolute value. I use absolute value for the limit, and I said absolute value of an minus l is less than some epsilon, given epsilon. So, because it might be like this, jumping up and down. Now, well, you might realize that this starts at negative 1. So it starts at negative. If n starts at 1, this starts at negative 1. I want this to start at positive 1. How can this happen? Well, it's very easy. If this n starts at 1, whatever, you have to look at this one and see wherever this starts. So for n equals, in this case, 1, this should be positive. How could this happen? Very easy. Just add or subtract 1 here. Sometimes they add, sometimes they subtract, no difference. So you add 1 here. So if you add n plus 1 here, then the first one will be positive, right? So the alternating, just by adding a 1 to this exponent here, you will get the other one, which starts at positive. So this one starts at 1, then minus 1/2, then 1/3, then minus 1/4, and so on. So it starts at plus 1. The same works if I write, instead of this, I use minus 1 to the power n minus 1, no difference. So, as I said, sometimes it's better to use this one, sometimes it's better to use this one, but as you see, they give you the same sequence. Okay, so let's see, let me write down some sequences for you. I can just take a look at it. Yeah, some properties. Okay, so we usually denote a limit of a sequence where we denote this thing. We use an going to L to mean limit of an as n goes to infinity is L. Okay, so properties of the limit say, suppose an goes to, say, some L, 1, say, and bn goes to L2, right? And let k be a real number. Now what do we have? Well, limit of, what happens to the limit of an or plus or minus bn as n goes to infinity? Well, it's very simple. Since both of them have a limit, it's not easy to prove, but it can be proved in higher mathematics using the definition that this is, in fact, this limit distributes over this, if they have limit. So that's an plus minus limit of bn. So it's like L1 plus or minus L2. 2. What happens if I multiply one of them by a constant? This is k. The k can come out, it has nothing to do with that limit. K, limit of L an as n goes to infinity, so that's k an as n goes to infinity, you can guess that it is in fact limit of an as n goes to infinity times limit of bn as n goes to infinity. So it is L1, L2. Okay, so it seems that if the two limits exist, then the limit in fact distributes over addition. Subtraction is like addition, then it also it's not distributed, it's say homogeneous in a sense, so this k can come out of the limit, and then it's in a sense it distributes over multiplication, and you can guess that it also distributes over division. So let me erase this and write number 4 here for you. Okay, so this one is limit of an over bn as n goes to infinity is a limit of an over limit of bn, or L1 over L2. This only happens if L2 is not 0, right? If the denominator doesn't approach 0. Okay, so that is one thing. Yeah, another one is this. Let's say 5. This one is a special case of something else. This is if I have a limit of, say, an to some power m, we'll use p. So p, and n goes to infinity. Then this p is like what? So it's like using number 3. It is limit of an times an, blah, 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 blah. But this p can be anything. I'm not saying it's an integer, it can be anything. Any number. And so this p comes out. So this is in fact limit of an as n goes to infinity to power p. Now there's something here. If the an's are negative and p is like say an even number, then negative to power even, not even number, sorry, if that's like a 1/2, for example. So negative to power 1/2 is a complex number. So we're not really in complex number zone, so let's assume that this makes sense. So let's assume that this makes sense. If an to power p is defined, or makes sense for all n. When I said define, let me put, because it is defined, if it is like negative 1 to power 1/2 is defined, then we define it to be I. But let's say that it makes sense. I mean, let's say it doesn't go out of the real numbers, say. Or sometimes it just doesn't exist. Okay, so this is also like an example of this thing can be this. So let me example from number 5. But let me think of something. I can think of something which is not 0. Let's see. Yeah, I can think of something. So let's say that if I have an is 1 minus 1 over n, say, and n starts at 1, 2, dot, dot, dot. So what is limit of an? Limit of an as n goes to infinity. That is limit of 1 minus 1 over n as n goes to infinity. What is the limit of 1? Well, I guess I didn't give you that as a... So limit of a constant sequence is the constant itself. Limit of a constant sequence is a constant itself. So limit of, say, as n goes to infinity of just simply k is just k. What is this thing? This is in fact k, comma k, comma k. Well, it's just k. It doesn't change. So the limit is, so it's limit of this one minus limit of this one if both exist. If both exist. So let's write up here the limit of 1 as this goes to infinity is 1, and the limit of 1 over n as n goes to infinity is 0. So this is in fact 1 minus 0, which is 1. Okay, so that's in fact using that property number 1. Okay, now as another example, let's say I want to find this limit. Let's say an is simply n and bn is 1 over n. And n starts at 1, 2, dot, dot, dot. But this one is divergent. Divergent means there is no limit. An is divergent. So let me write here what divergent means. Means no limit. Or limit is plus minus infinity. So if it's no limit, if it doesn't have any limit, we just say the limit doesn't exist, right? So no limit, in fact, also means DNA does not exist. This one is most often divergent is used for this one. This one is the limit exists in a sense, but it's not a finite number. So divergent is used for this. And convergent, as you can guess, is convergent means limit exists and is finite. Okay, so let's go back to like Calc 1 when we define divergent and convergent. I should have said this first, but I think that makes more sense if we say divergent first, then convergent. So divergent means either there's no limit, which we usually write DNE, or it's plus minus infinite. Now, what is, well, let me give you this one, then I will talk about the DNE, what DNE means in this context. This one is a convergent. It goes to 0, right? So well, let's look at this. The limit of an and bn as n goes to infinity will be like a limit of 1 as n goes to infinity, and it's 1. So this tells me that it can happen that one of them is divergent, the other one is convergent, but when you multiply them, you get a convergent sequence. So that assumption is essential over there to say that both of them are convergent when this happens. And it doesn't go the other way around. So you cannot say if this limit is convergent, if the limit of this exists, then both of them are convergent. No way. So most of those, I can't think of the first one. The first one is also true. So those theorems don't go backwards. But anyway, now I was talking about the DNA. Let me erase this and give you an example of the DNA in this context. So DNA is something like this. Say a sequence, well, an is minus 1 to the power n, and let's say n 1, 2, 3, dot, 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 and this sequence is what? Minus 1, 1, minus 1, 1. minus 1. Does it go anywhere? No. It's just alternating, jumping up and down. Or you can define this to be, I don't know, let me, another case of dn might be, if I write an is, can I use sine or cosine n pi, 0, 1, 0, yeah. So it's in fact the same as that in a sense, cosine of n pi. And n starts at 1, 2, 3, dot, dot, dot. What is this? Cosine of pi is negative 1. Cosine of 2 pi is 1. 3 pi negative 1. 1, negative 1. In fact, these two are the same. Another way of writing negative 1 to power n is, in fact, writing is at cosine n pi. So negative 1 to power n, in fact, is cosine n pi. So these are the limit dna. Limits does not exist. Okay, the limit does not exist. Okay, so that's the case that the limit does not exist. Most often we just write dne rather than saying it's divergent. Divergent, as I said, is mostly used for the second one. And even some people just use it for the second one, not the first one. But okay, that's just some technicality. So this one, well, I can just simply say an is n squared. So this is 1, 4, and 9, and 16. So as we see, this limit an goes to positive infinity, right? So that is divergent. That is what we call divergent. But we can write it. We can say that an in fact goes to a positive infinity, which means it gets larger and larger and larger without any bound. Or the other way around, it can get smaller and smaller and smaller without any bound. Okay, so well, we can say lots of things about sequences, and as I said, I don't want to emphasize too much because we immediately jump on series, and we use them to define certain things for series, but eventually you will be mechanically, without, that's bad to say, but without knowing what you're doing, you just can mechanically find whether a series is convergent or divergent or some other things. But anyway, so let me see if there is anything else here which I have to discuss before I jump to next. Yep, interesting theorem. Some people call it squeeze. But squeeze have two Z. SQUEEZE, not double E. Squeeze or sandwich. The sandwich theorem is telling us if, say, an less than equal to, say, cn less than equal to bn, say, and limit of an as n goes to infinity equals limit of bn as n goes to infinity equals L, then limit cn exists and is equal to L. Okay, so you can tell from here that this limit, as it goes to infinity, this say inequality still exists. So as you go on and on and on, this happens for every n, right? So if n gets larger, if this gets larger, this one gets larger, and this should get larger, and should stay between them. So in the limit, we can say that this n going to infinity of an is also less than equal to limit as n goes to infinity of cn, and less than equal to limit bn, n goes to infinity. And if we can prove this thing, then this is L less than equal to Cn as n goes to infinity, less than equal to L. So what does this mean? This is bigger than L and less than L, so it is equal to L. So that's the only way this can happen. So that's a squeeze or sandwich, and you can tell why it's called a sandwich, because this is like sandwiched between these two. Okay. And then there's another one, another interesting theorem here. There are in fact too many. I will just mention them and give you some idea how this thing can happen. So this is like a statement of the theorem, and this is like I'm not saying it is proof, but it is how you can think of this and why it happens. The other theorem is this, which helps a lot. In fact, all of them help studying sequences, and that is this. If limit of absolute an, n going to infinity, exists, or let's say if zero, not exists. If it is zero, not any, then a limit of an is also zero. Exists and is also zero. Now, a good example of this is in fact the one that I mentioned. So if an, say, is minus 1 to power n, 1 over n, okay, then absolute an is what? Is simply 1 over n. Absolute value gets rid of this negative 1 to power n, okay? And we know that this one exists. This limit of an as n goes to infinity is in fact limit of 1 over n as n goes to infinity, and that is 0. So this implies that the limit of absolute an itself as n goes to infinity is also 0, which is limit of minus 1 to power n 1 over n as n goes to infinity is also 0. I mentioned this one, but I showed you a picture that it goes up and down above and below the x-axis, but eventually it gets closer and closer to the x-axis, and it is 0. But in fact, to prove it, we can use this. We can use this theorem, and in a sense, it's saying that if the positive, if the positive sequence, or let's say the sequence without negatives, approaches 0, then the other one should also approach 0. If that approaches 0, this one should also approach 0. The proof is very simple, but I'm not going to prove that, but using the definition of a limit is very simple. Anyway, so let me erase this thing and see if there is any other theorem or example, nice examples here. And before I start something more, say, interesting than this pure mathematical things. So, another theorem, if f is continuous at L, if lim of an as n goes to infinity is L, and the function f is continuous at L, then this is important, limit of the function applied to an as n goes to infinity is in fact f of L. Okay, so if that an the limit exists, then this also. So let me give you an immediate example here. Say if I have say if an is 4 minus 1 over n. And let's assume that n starts at 1, it cannot start at 0. Then let f of x be square root of x. Then what happens? And look, when n starts at 1, this is always positive, right? So the square root of an makes sense. So this gives me what is the limit? Limit of this 4 minus 1 over n. Now students usually they just bring this down. They say, okay, the inside is 4, so the limit is in fact square root of 4, which is 2. But why can you do that? Why can you bring this limit inside? In fact, that's the meaning. You are bringing the limit inside. So this L is limit of an. It's in a sense is saying that the function f and the limit they commute. So you can bring that limit inside this function, if that function is continuous at L. So this means that if I use this notation here, it is equal to bringing this limit inside and goes to infinity, and this is 4, which is 2. Okay, so most often when you see things like this, in fact, you can apply this theorem without even being concerned about this fact that this function is continuous at L. Usually that function is continuous. Like this square root of this function is very nice and continuous. Yeah, you might see like polynomials, they are continuous everywhere. Well, this is not defined for negative numbers, but for positive numbers or non-negative numbers, it's continuous. So most often you're dealing with continuous functions, unless you have like tangent, for example, which is not continuous at certain points. But most other functions that you deal with are continuous. So this, in fact, this is a nice theorem which is quite useful, and you will see that a lot in is this, in fact, saying that the function f and the limit they commute, they switch. They can switch positions. Okay, so let me erase this. Oh, yeah, I know this section has lots and lots of. What else? Okay, two things are important here. One is the limit of, which I use this one, but this is like a theorem which can be proved. It's about the limit of r to power n. Limit of r to power n as n goes to infinity. What is it? If r, so it is a 0 if r, absolute r, is less than or equal to 1. And it's infinite, but it can be plus minus infinite or divergent, say, if this is bigger than 1. But let me give you an example and you will so you get a feeling what it's saying. So what is limit of 1/2 to power n? This is 0. Why? Because absolute value of 1/2 is less than or equal to 1, right? And you can look at what this thing is. This is say for n equals 1, it's 1/2 1/4. This is in fact a geometric sequence, right? 1/8 and 1/16, dot, 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 and this goes to 0, right? So this is in fact an example when we have this situation that this R in fact is absolute value is less than 1. Now, what does it mean? The absolute. Let me give you another example. So if I have this thing, what happens to this? -1 to power n, 1/2 to power n. This is also a geometric sequence. But what is, you can write this in this form, we can write it as -1/2 to power n, right? That's the same thing. You see this minus here, you can bring it out, that's -1 to power n, 1/2 to power n. So what is this? In fact, I have -1/2, absolute value is less than or equal to 1, right? -1/2 absolute value and 1/2 are the same. So this also is 0. Okay, so whatever this thing is, if the absolute value of this is less than or equal to 1, then it is convergent. Now, I said that's not true, so I can just say it is convergent, right? But for this one it is 0. What happens if R is 1? Well, R equals 1. When R equals 1, it is simply 1. R equals 1, it is simply 1. And for R equals -1, does not exist. That's just amazing that for R equals -1, it does not exist. Well, so I guess that's enough, and I don't want to pay too much attention to the different cases, but in fact, in the book, it doesn't say anything. It says something about 1. So increasing and decreasing. So the definition, there are 2 definitions, and then the monotone definitions. So 1 is increasing, decreasing. We say that an is increasing if what? An is less than or equal to an plus 1. And it is strictly increasing if the equality is not there. Like what? Increasing like, say, like an equals 2 to power n, right? So 2 to power n is less than or equal to 2 to power n plus 1. And B, it is decreasing, an is decreasing if the other way around. Like what? Like an equals 1/2 to power n, right? 1/2 to power n is less than or equal to 1, is bigger than or equal to 1/2 to power n plus 1. And that's in fact the reason this goes to 0, right? Because it's getting smaller and smaller. So this one goes to 0. In many cases, not always, in many cases it goes to 0. So that's increasing, decreasing. There's another definition here. And also, then we say C, AN is monotone if it is either increasing or decreasing, right? And I see that the book is not using strictly increasing or strictly decreasing, so let me use the notation here. So I'm not going to use that strict, but you might see that notation somewhere. It says increasing, it also talks about strictly increasing or strictly. Strictly means there's no equality here. But I don't see that here in this book, so let's stick with what the book has. So it doesn't use the strict here. So it just defines increasing as this and decreasing as this. And number two is, so in fact this monotone is important here. If we didn't use that, we should have said monotone means strictly, say, but so those are just technicality, and this is not such rigorous and bounded. Bounded sequence is this. We say that AN is bounded above if there is an N such that absolute AN is, well, this should be positive, absolute AN is less than equal to this N. Okay, so, and the B, we say that AN is bounded below if this AN is bigger than or equal to this N for all N. And all N. Now when we say all N, it doesn't mean that it should start at 1. So if some of the terms in a sequence it doesn't apply, some of them are just jumping up and down, say, but at some point it becomes so nice, so it's less than N, then we can truncate. You can always truncate that sequence and say, I don't care about this, because then you can use the rest of that. The rest of that become useful. But let's stick with this thing, and this is bounded above and bounded below, and C, a sequence is bounded if it is both bounded above and below. Both bounded above and below. So bounded, in fact, means that I can write it here, AN is less than or equal to some N, bigger than or equal to some, say, M. Okay? And in this case, well, because I'm using absolute value, so I can just say this is both M and N are positive. Otherwise, if I'm just using AN, I can say that this is, so some people just say it is between two numbers, AN and N, right? It doesn't have to be absolute value. Let me see if the book uses absolute value. No, the book doesn't use absolute value, so let's not use the absolute value here. So we say this is bounded above and this is bounded below. So this doesn't make sense here. So I could, in fact, if I use absolute value, it's GL. nonsense. So this using absolute value means it's bounded both above and below. So yeah, I don't need absolute value here. So yeah, no absolute value. And that makes sense. So anyway, this is bounded if it is like that. And what can we say? In fact, this is a monotone convergence theorem, famous theorem which we are not going to use, but it is used extensively. Well, let me write a statement carefully for you. And another definition, so the third definition is a sequence is that's not the theorem, but that's the monotone convergence theorem. We say that a sequence is convergent if every monotone bounded sequence is convergent. So what happens if it's both monotone and say bounded? Let me show you in picture what's happening. So first of all, bounded. Bounded means that there are like two numbers. It doesn't have to be positive or negative. It can be either. So there's this m here, and then n here, and the sequence is bounded between these two. So the sequence is like this. Okay? But that's not enough. Being bounded is not enough. Why? Just look. The sequence minus 1 to power n, minus 1 to power n is bounded. But not convergent. So this sequence is bounded, but it's not convergent. So what makes that bounded sequence convergent? If it's either always going up, not always, but it can start going up or down at some point. So it might jump up and down, then start going up or down. So let's say it's like this, and then suddenly it is like this. Or like this. So this tail of the tail of the sequence can be jumping up and down, but then the other tail, the infinite tail, should be either going up or going down. So if this happens, then, and this is in fact this one, this is not monotone. It is bounded, but not monotone. It jumps up and down. It doesn't go either up or down. So if this happens or this happens, then it has. I'm not saying that the limit is m or n, but the limit, in fact, is between these two. The limit is also between these two. It can be this one or this one, depending on whether it goes up or down. But in any case, we can show that it is between these two bounds. Okay, so I guess that was the last thing in this nice section, and the next time I have to start. In fact, I just talked too much, so we'll start something which, in fact, we will be using and we will be discussing more than just sequences. This section is, as I said, is long and technical, and we are not really using that too much in this course. Okay.